One of the first things you should do in this case is take all the residuals in the aggregate and plot the blooming things. And so the first thing we're going to see is a plot of all those residuals. There are 24 residuals. Now let's look at them. You know, they're not bad. You know, that's a pretty good collection of residuals, really. There are 24 there. They do have a sort of normal appearance. There doesn't seem to be any bad mavericks or anything of that sort. You want to be a little careful watching these residuals. Remember, they're constrained. There'll be a certain tendency for them to coalesce and compact because there are only 20 degrees of freedom, although there are 24 dots on that graph you see there. One thing we do in studying residuals, we check the residuals off against the individual treatments. And so let's actually plot the residuals within each treatment and see if there's anything, any hanky-panky going on among the residuals in that case. So we're next going to see the residuals for each treatment. There are the 4 residuals for treatment 1. Golly, that's nicely balanced. There's hardly anything going on there. Here come the residuals for treatment 2. Let's see the residuals for treatment 2, shall we? And now let's see the residuals for treatment 3 and for treatment 4. And once again, we're looking for non-normality. We're looking for a change in the variability, the change in the variance of the observations we move from treatment to treatment. We have so few observations here that it's difficult to really declare that anything is going on except, you know, just the standard randomness we'd expect from normal deviates. One important thing to check with respect to the residuals is the following. When you do an experiment in random order, you should record in time order the experiment, and so that when you get the residuals, you can plot the residuals in time order. Because we're always afraid that something's going to force the residuals to move up and down in some particular pattern. And here we see the residuals plotted in time order in treatment 1. I don't see any trend going on there. How about in treatment 2? And in treatment 3? And again in 4. There are the residuals plotted in time order. And what I'm looking for here, gang, is some tendency for the residuals to cluster or to grow as they move down in time, as the observations are, in a sense, older in the experimental sequence. There's nothing going on there in trending at all. I should remind you that there's sort of an inside joke among statisticians. 3 points in line make a trend, and we're all supposed to break out great laughter when you see that, hear that. But you'll notice there in treatment 2, in the early part there are 3 dots in a row. That's the barest, humblest symptom of a trend, and I wouldn't knock myself out planning a trend there just because those 3 residuals did fall in a line like that. So there's no real information here that there's any time dependency to upset our assumption of independence. Now there's one other way to plot the residuals which is very interesting, and that has to do with plotting the residuals against the predicted values. And so we're going to see that unusual chart right now. Now the predicted values for each one of the treatments happens to be the average for each treatment. In other words, if I were going to predict what's going to happen in treatment 1, I would predict a 61, because that was the average for treatment 1. And you'll see here that the residuals are plotted along the vertical axis and the estimated values along the horizontal axis. And you can see the residuals being plotted here. And what we're studying and what we're looking for here is a change in the variance as the magnitude of the response grows. Sometimes when the observations, when the response gets larger, the variance increases right along with the response, and that would mean we'd have non-homogeneous variance. And of course you can have it the other way around. When the response gets smaller in magnitude, the variance increases. We're looking for that sort of thing in this analysis, the residuals, and it's not there. That variance is pretty much homogeneous across the responses. And so I come to the conclusion, finally, that yes, indeed, our residuals do, in fact, oblige the assumptions made. There's no information here which disenchants me from either the model or the assumptions. And so I now conclude that I can go full speed ahead, estimate the variance off the blast line analysis variance table, and do my F tests and anything else that becomes subsequent in our statistical analysis. Well, let's do that and get that off our back, shall we? Let's get the mean squares and the expected value of the mean squares in this case. And so way down there at the bottom we have for our mean square our estimate of the variance. If I divide the degrees of freedom into the 112, I get an estimate of the variance equal to 5.6. Now if I assume that the taus are all equal to 0, then that 228 with its 3 degrees of freedom will provide me another estimate of the variance, because all I've done is partition 23 degrees of freedom into 2 chunks. And that would estimate sigma squared, only if this assumption is true, that all the tau sub j's are equal to 0. So that's a conditional. We say it estimates sigma squared given that particular fact. Well, here we are back at the old stand. I've got two numbers running around claiming to estimate sigma squared. The 5.6 says I estimate sigma squared, and the other value, 76, says no, I estimate sigma squared, and I'm just as good as you are under the hypothesis that tau's are 0. So what do I do when I have two estimates of the variance? I can check them out, right, by using the F statistic. And so I've done that. We take the F ratio in this case, and if we take the ratio of those two estimates of the variance, the 76 over the 5.6, we'll get an F with 3 and 20 degrees of freedom, 3 in the numerator estimate and 20 in the denominator estimate of the variance. That comes out to be 13.6. And now, of course, the $64 question is, what's the probability of observing such an F? Well, I looked up the critical value of F at 3 and 20, leaving 5% in the tail of the curve, and it turned out to be 3.10. And my observed value of F is way the devil out in the tail of that skewed curve. It's way out there at 13.6. Hey, that is a rare event. All right? And so what's that lead me to do? I take the attitude that rare events don't happen to me. Well, they do rarely, but, there are rare events. Events like that just don't happen. And so what that does, it casts an aspersion, a reflection on that particular hypothesis. And so I end up thinking that there is really something wrong with the hypothesis that those tau's are all equal to 0, and I reject the hypothesis. And I believe instead that the 76.0, yes, it estimates sigma squared. Some of that is certainly due to the intrinsic variability of the data, but other portions of it must be due to the fact that those tau sub j's are really non-zero. They're really there, and they're squaring themselves up and getting in and inflating that estimate of the variance. And you notice that there the individual tau sub j squared, the individual treatment effects have been squared up, and each one has been multiplied by the number of times it appears, as we noticed when we played around with our detailed analysis using that box we had just a moment ago. Now, if you wanted to, you could take this estimate of the variance and construct a reference distribution for your averages and attempt to interpret what's really going on in the data. Okay? Let's go back and think about that problem, that experimental design, another time. And you can imagine a situation in which you plan this experiment. You've got 4 heat treatments you want to do, and you've been talking to the men on the floor and so on, and one of them says, well, gee, Mondays are miserable around here. The equipment doesn't work on Mondays. We hardly work on Mondays. It's a miserable day. All the yields are going to be down on Monday. And Wednesday's a great day. That's a blooming day. The yields are always great on Wednesdays. And Fridays, well, they're always suspect. And so what he's saying in this instance is that there's a day-to-day variability. Here's an assignable source of variability. And it's a kind of a source of assignable variability which we can take out of our analysis by proceeding in the following fashion. Let's run the 4 treatments randomly on Monday. See, Monday would represent a block of 4 runs, and so we'll run the 4 treatments randomly within that block on Monday. Now, suppose it's really true that all the yields on Monday are down, okay, way down. Well, so what? That would just mean that the differences between those 4 treatments would in a sense be taken, they'd all be down. And so any differences would be adjusted by the fact they're all down. And suppose they are all up on Wednesday. The same thing, they'd all be up. So any comparisons I made between those treatments would be, therefore, in a sense, taken out. Well, let's look at this randomized block design. I have the randomized block design with another collection of data over here. It's a randomized block. The experiment's been blocked, and we've run the trials, the treatments inside randomly. Here's the appropriate mathematical model. It's additive. And we say the block effects, if they're there, add on, just as the treatment effects add on, and just as the errors add on. And we make the usual assumptions about the errors. Here are the 4 treatments. Here are the 5 blocks, Monday, Tuesday, Wednesday, Thursday, Friday. On Monday, I randomly compiled these data. And there are the averages for the 5 days, and down here are the averages for the 4 treatments. And here's the grand average. Suppose now I ask you to get the estimate of what happened on Monday. What's the Monday effect in this case? Well, the average for Monday was 92, and the grand average is 86. So apparently, in this case, Monday's a very good day, if high yields mean good. And so the effect for Monday is +6. What do you notice about all the effects if you calculate them all for across the blocks? They sum to 0, see? And here are the treatment averages, and here are the treatment effects. Okay, now, Let's return to the same kind of a detailed analysis of the individual observations that we did before when we had the completely randomized design. And behold, I have here, like magic, my square prism has changed into a pentagonal one. And here are our observations. There they all are. Right, and I'm going to take those observations and break them out into their individual components. And let's play that game again. Let's pick one of the observations and follow it around. Let's pick the 77 and see what happens. The 77 equals, now the Yij equaled the mean, which we estimated with the grand average 86. See, plus, now let's estimate the block effect. That's in Tuesday, the second block. And Tuesdays apparently were down by 3. That's what we estimate them to be. Pick up a -3. And now let's go ahead and worry about the treatments. That was in the second treatment, and the second treatment had an effect of -1. Okay? And now finally we've got to make the whole thing add up. There's an equal sign back there, and the residual in this case turns out to be a -5. So there you see the fracturing of the observations into their component parts. All right, let's do the same thing with the sums of squares. If you take the sum of squares here, you get 148,480 with 20 degrees of freedom. And, you know, moving on around here, here's the correction factor. Take those 86s, square them up and add them up. You get that particular quantity, 147,920. If you take the blocks contributions and take their sums of squares, it comes out to 264 with 4 degrees of freedom. And the treatment sum of squares, 3 guesses, comes out to be 70 with 3 degrees of freedom. Take those sums of squares, and finally the residual sum of squares will come out equal to 226 with 16 degrees of freedom. These 12 degrees of freedom. These residuals are constrained enough, so there's only 12 degrees of freedom remaining. And so once again, we can look at the analysis of variance table now, the fracturing of these sums of squares into their component parts, because they also add up. Okay, let's do that. It'll only take a moment to do that. Here's the corrected sum of squares was 560, and it had 19 degrees of freedom. The block sum of squares is equal to 264, and it had 4 degrees of freedom. And the treatment sum of squares was 70, you may remember, with 3 degrees of freedom. And the residual sum of squares turns out to be, by subtraction, 226 with 12 degrees of freedom. Okay, now let's imagine we've studied our residuals to find the aberrant observations or whether or not the assumptions have been met. And let's imagine that they are, and so the mean square, if I take the 12 degrees of freedom for the errors and divide into their sum of squares, I get 18.8. That's the estimate of sigma squared. And if I make the assumption that there are no treatment effects, 3 into 70 would give me a second estimate of the variance, given that the taus are all equal to 0. And now I'm ready to do my F test. I'll have an F with 3 and 12 degrees of freedom to check out on that hypothesis. And when I do that F ratio, I pick up a 1.24. And of course, I wonder now, is that a critical value of F? And I looked up the critical value of F with 3 and 12 degrees of freedom, and it's 3.49. This is less than 3.49. It's well inside the acceptable values of F. And so there's nothing in these data which would contradict the hypothesis that tau sub j's are equal to 0. Back to the laboratory, gang. Get some more data, or maybe you better think in terms of a keener experimental design in an effort to decrease that intrinsic variability. So by golly, if there is anything going on between those treatments, we're going to be able to find it out. Okay. Well, you've seen us break out the analysis of variance. In this case, we have made one essential change. When we deal with the randomized block model, of course, our model changes, and we had to have a model which accounted for the mean, the block effects, the treatment effects, and the residual effects. All right. Blocking is important, and it's an essential way of increasing the precision of the experimental procedure. And how do you run a blocked experiment? You must remember that some aspect of randomization has to attach itself to every experiment. And so what did we do on Monday, gang? We took the data on Monday, and who did we do first on Monday? Right? Hit me. See? We did C first on Monday, treatment C, and then late Monday morning we did this particular treatment, D, and then first thing that afternoon we did B, and finally we did A. And so it was on Tuesday and Wednesday. Pick a card.